Welcome back to the Facts Matrix. Today, we're diving into a world you never see, but you use every single day, the quantum world. From your phone and your GPS to lasers, atomic clocks, and even new kinds of computers, the rules of the tiniest particles are quietly running the show. So, how did a theory about things smaller than atoms end up controlling black holes, keeping time, and guiding your car through traffic? Let's find out. A couple hundred years ago, scientists saw the universe as a giant, perfect machine. Matter was made of particles, light was made of waves, and everything followed predictable laws. If you knew all the starting conditions, you could, in theory, predict the future exactly. But in the early 1900s, that certainty started to crumble. Light sometimes acted like a wave, and other times like a stream of particles. Electrons inside atoms didn't orbit smoothly. They jumped between energy levels in sudden steps. The old rules didn't fit anymore, and out of that mystery came a new set of laws. Quantum mechanics. Here's the first big shock. At the deepest level, the universe doesn't behave like a machine. It behaves more like a game of chance. In everyday life, when something looks random, like rolling dice, it's only because we don't know every detail. But in the quantum world, even if you knew everything, some things are still truly unpredictable. Take an electron, for example. Before you look at it, it's not sitting in one exact spot. It's spread out in a cloud of possibilities. This is called superposition. It's here and there and a bunch of other places all at once. The instant you measure it, that cloud of possibilities collapses into one result. The electron shows up in a single location. The weird part is that quantum physics doesn't just describe what we don't know, it describes what reality actually does. The universe itself seems to be rolling the dice. That sounds strange, but it's also what makes our technology work. Your smartphone, computer, and television all depend on tiny switches called transistors, and those only work because we understand how electrons behave according to quantum laws. No quantum physics, no transistors. No transistors, no computers, no internet, no GPS, and no fax matrix. So right now, you're literally watching this because quantum mechanics works. Quantum physics even keeps time for the entire planet. Modern timekeeping uses atomic clocks which rely on the behavior of electrons inside atoms. Electrons can only occupy certain energy levels, like steps on a ladder. To move between those levels, they need to absorb or release energy in exact amounts. That specific energy corresponds to a frequency, like a note played perfectly in tune. For a cesium atom, that note vibrates over 9 billion times per second. By counting those oscillations, we define 1 second. Those same atomic clocks orbit Earth in GPS satellites. Your phone receives time-stamped signals from them, compares the timing, and calculates your location. But time doesn't flow at the same rate everywhere. Clocks in orbit, where gravity is weaker, tick slightly faster than clocks on Earth. Without constant corrections for that difference, your GPS would send you to the wrong place. So every time you follow directions, you're depending on quantum physics and Einstein's relativity working together. Quantum physics also gave us one of humanity's greatest inventions, the laser. A regular light bulb is like a crowd of people yelling different notes at once, bright but chaotic. A laser is like a perfect choir, every voice singing the same note, in sync, in one direction. That harmony happens through stimulated emission, when one photon of light triggers an atom to release another photon exactly like it. Inside a chamber with mirrors, those identical photons multiply until a pure, focused beam escapes. Lasers perform eye surgeries, scan groceries, cut metal, power internet signals through fiber optics, and even entertain cats. But they also helped us do something incredible: detect ripples in space-time. When massive objects like black holes collide, they create tiny vibrations in the fabric of the universe called gravitational waves. Scientists built an instrument called LIGO, which uses lasers and mirrors miles apart to detect those tiny distortions. Under normal conditions, two laser beams cancel each other out perfectly, but when a gravitational wave passes through, the light shifts just enough to leave a faint signal. In 2015, LIGO detected one of those ripples, the echo of two black holes merging over 1 billion light-years away, releasing more power in a fraction of a second than all the stars in the universe combined. And we heard it because of quantum lasers. Another strange quantum effect is entanglement. Imagine a machine that spits out pairs of coins. You take one, your friend takes the other, and you flip them far apart, even across the galaxy. Every time you flip yours, theirs matches perfectly, as if the two coins are secretly connected. That's what happens with entangled particles. Their properties are linked, no matter how far apart they are. Einstein called it spooky action at a distance. But experiments keep proving it's real. Today, entanglement isn't just weird. It's useful. Scientists use it in quantum communication, encryption, and advanced measurement systems. And it's the key to the next leap in technology. Quantum computing. A normal computer uses bits, zeros, and ones. A quantum computer uses qubits, which can be 0, 1, or both at the same time thanks to superposition. When qubits interact through entanglement, they can process information in parallel, solving certain problems far faster than classical computers ever could. But quantum computers need extreme conditions, near absolute zero temperatures, to keep their delicate quantum states stable. Companies like IBM and Google are racing to perfect them, not for video games or spreadsheets, but for simulating molecules, designing new materials, and solving optimization problems far beyond today's machines. The deeper we go into the quantum world, the more we realize it isn't just science fiction. It's the foundation of modern life. Every phone call, every GPS route, every laser surgery, every byte of data you stream traces back to those invisible rules written at the smallest scales of reality. And maybe the strangest part is how normal it's all become. We live in the quantum age. We just don't notice it. So the next time your phone tells you where you are, or you see a laser show, or you hear about scientists detecting a ripple in space-time, remember, that's quantum mechanics at work. The tiniest forces in nature are quietly shaping the biggest parts of our world. Well, there you have it. If you enjoyed this journey through the invisible side of reality, make sure to like this video and subscribe to the Facts Matrix. Your support helps us to continue to bring you a new video each and every day. Thanks for joining us on this journey. See you next time when the Facts Matrix brings you more facts on people, places, and beyond.